This video will be breaking down how to do the Experimental Design FRQ. So I'm looking at last year's FRQ for the Experimental Design. So this is the one that they had last year. So it's a wheel, axle, and hanging block on the floor. The first question asks us to find the quantity to be measured and write that down, the symbol for the quantity, the equipment for measurement, and to write down the procedure. So the question asks us to design an experimental procedure that students could use to compare the increase in blocks translational kinetic energy with the decrease in gravitational potential energy of the block Earth system as the block falls. So what I did for this was I did the quantity to be measured as the mass of the block M, equipment necessary, balance, distance fallen, Y, meter stick, and the velocity of the block via B, motion sensor. So my number one was to take the blocks off the wheel and measure the mass using the balance. 2, measure the height of block from floor when block is at initial position. 3, place a motion sensor on forward to measure final velocity. And 4, drop block from initial position and record outputs. And 5, repeat steps 1 to 4 3 times. You need to be very specific in how you write these. So you can't just say take block off wheel and weight. You need to do and measure mass, because mass and weight are not the same thing. And you need to do what you're using to find that. So that's why I said measure height of block from floor when block is up in initial position. I should add using meter stick. And then 3, place motion sensor on floor to measure final velocity. And then 4, drop the block so it tells you what to do. And 5, you need to add this part to repeat steps 1 through 4 3 times. This will get rid of experimental error. And then the next part asks to explain how to determine the kinetic energy to block immediately before it hits the ground. You have to use what you did in quantities to be measured. So I did use measured mass of the block and the final velocity from motion sensor before it hits to calculate kinetic energy before contact is equal to 1/2 mv. This would be mv of block squared. So that would have gotten the point for that. And then C, all C asks us is to draw a line, a curve to represent rotational kinetic energy. It gave us the full line was kinetic energy gained during fall, and the dash was change in potential energy of the block wheel Earth system. So here it showed us that the change in the potential energy was -4. So we know our mechanical energy is 0.4. So our kinetic energies have to combine to be equal to 0.4. This looked to be around 0.1, so I went to just above 0.2. So I get around 0.1 plus 0.2 is equal to 0, not 0.3, my bad, is equal to 0.4. Yeah. And then if we look at the sample responses for this is all you have to do for this question. Just around 0.3. So this should actually be a little higher up. In question 4, it gave the graph below shows the rotational kinetic energy in respect to omega squared, omega being the rotational velocity. And so the first part it asks is just draw a straight line that best represents the data. So a line of best fit. It doesn't have to be entirely the same. So this is what I just used. And then II as to using the line drawn, calculating the experiment value for rotational inertia. It gives us in the cheat sheet that K of R is equal to 1/2 rotational inertia times omega squared. So 2 times kinetic energy of rotational divided by omega squared is going to be equal to I. So 2 times 1.2 divided by 35. I just use this point around here. They don't really care if it's not exact, but if you want to be safer, you could take it like exactly where 130. So I get 0.685 is equal to I. Then I rewrote it over here. I is equal to 0.0685 joules divided by radians per second squared. So you have to write the unit at the end to get the final answer. And so this would have gotten a 12 on the Experiment 3 FRQ.